Hello. Hello. Hi. Can everybody hear me in the back? All right, good. We'll get started. My name is Ash Palgat. I'm Senior Director for Cloud Marketing from Mellanox Technologies. And I have with me Mark Iskra, who is Technical Marketing Expert from Nuage Networks, part of Nokia. And today we have a very exciting topic and talk to deliver here at Open Infrastructure Summit. And the talk is highly efficient edge cloud data center for 5G. And so we have a lot to cover, but it's just a little context. If you've seen the talk that just was delivered by the ByteDance folks next room, there's some overlap from that, but I think we'll be talking a lot more about the edge cloud. So some of the concepts might be familiar for you from there. So what we'll be covering is telco cloud evolution. As you know, the telco cloud has, from the traditional central offices where everything was very appliance-based, things have morphed into SDN, NFV, more programmable networks, and that's from the core data center standpoint, so central office morphing into core data centers. But then that innovation of SDN, NFV is now percolating all the way to the edge and far edge as well. So we'll talk about what those requirements are. Then we'll talk about how do you build a holistic edge cloud data center for VMs and containers, microservices model as well as the virtualized functions model. How can it be done seamlessly, and what are the technologies that are really going to be key to kind of be to achieving your efficiency across the entire network. And the third is a interesting concept that we are introducing for the first time here. It's called as how do you reduce the cost of your edge data centers. A lot of times, the operators are under pressure in terms of improving their margins, and it's very important to reduce the cost. So that's the third concept that we're going to talk. So it's all about efficiency at the edge. So let's talk a little bit about what's happening, the transformation in terms of managing lower latency and cost trade-offs in a layered architecture of a telco network or a telco cloud. You can see that in the central data centers today, on my right-hand side here, you typically have, smaller number of data centers. These are large data center, football-sized data centers typically. You have, high power budget requirements. Of course, the latency to reach that, central data center or the core data center is pretty high. As you move towards the left, as that's happening now more and more, you see that on the edge side of the data center, the requirements are more stringent. But then you have thousands and thousands of sites now that are available. These can be as a colo facility, as a colo data center. It could be far edge, which can go into a radio tower itself, cell tower itself. So all these are kind of the new evolving requirements for the data center. This is kind of pretty well understood domain, and we've achieved a lot of efficiency here. But I think now that same efficiency, if you want to transform it to the edge, the constraints are getting more tighter, right? That's the main key thing here. The latency, for example, on the far edge is of the order of less than 1 million seconds round trip time, which is what the 5G is needing. At the edge data center, it's about 4 to 10 milliseconds. So all of these are very important constraints. You need to understand the power has to be really low. The footprint of the network has to be really small. That's not the case here on the core side. And you have thousands and thousands of sites, so it's also important to manage all of these sites through a centralized SDN control plane. So all of those are very different paradigms and requirements for the edge cloud data centers. So let's talk about how SDN has changed the world in the telco cloud, and we'll come back to how it applies to the edge cloud as well. But essentially, as we started with a bare metal kind of environment, we had all these CPU cores available for your applications. And this is your traditional network. It could be an appliance. It could be a bare metal environment. There's no virtualization here, which means that everything is applicable to you. You can run it as you like. But then we realized this is not scalable. This is too expensive. It's not really flexible. It's not efficient. And so we added something called a software-defined everything. And what happened in the software-defined everything world is you started adding more abstractions. There was a talk, or there was in one of the keynotes, people talked about abstractions. That's truly right. You have the hardware, but you add more abstractions so you can achieve more efficiency out of the hardware. And what that means is you added cores that are dedicated for virtualization, be the SDN, SDS, software-defined storage, software-defined networking, software-defined security. These are the red ones. You added cores for pretty much anything that could be done in the software that are going to be eating up that are going to be eating up the total number of cores that you have. So essentially what you have is from a bare metal kind of environment, now you're going to an environment where there's very few cores available for your tenants or for your application developers. And that's not scalable because while achieving flexibility, programmability, and agility, what you sacrifice is performance and efficiency. And that's really not scalable, again, for the telco networks or the telco clouds. Essentially, what we need is something like this, which is going back to it, but something that can be still done, all of these functions can be still done in a much more efficient way. And that's where I think SmartNICs are a rage right now in the market. As you know, SmartNICs are not your regular NICs. They're not your regular 10, 25, 40 gig, 50 gig NICs. These are your SmartNICs that are not only offering you high speed up to 200 gig, but can also offload all of these functions for the SDX into SmartNICs, can even do security in the SmartNIC. And that's basically the promise of the future in terms of achieving it's kind of, I can bake my cake and I can eat it too, because I have my cores available for my application developers, but also have the faster network that is more efficient. One of the, we talk about OVS a lot here in the Openstack community, in the OS community, and that's really because OVS is a really popular virtual switch out there. And as you can see, OVS is a virtual switch that's all part of the hypervisor. It's really a great virtual switch if you look at it because it has support for all the layer 2 and layer 3 networking functions. It can even go layer 4 to layer 7 functions, right? You can do NATing, you can do firewall, load balancers, et cetera, right? So it's really flexible, programmable, open flow based programming model, so it really lets you program it. But the issue here is that OVS by itself, we have a love and hate relationship with OVS. The love is because it's really great with respect to the features, the community support. And the hate is because, all of the red things here that I said on this slide, which is, it has awful packet performance, which means it can only deliver 1 million packets per second for 2 to 4 cores, right? That's really eating a lot of cores and not so much performance. It consumes a lot of CPU. For 30 gig, if you have a 100 gig NIC, to reach 30 gig NIC, 30 gig throughput, it will pretty much wipe out half of your machine if you have a 24 core machine. And again, the latency issues can cause user experiences, poor experiences, which is not really great. And so really what we need is something that, something can offload the OVS processing, can still keep the software-defined aspect of OVS without sacrificing the performance and the efficiency. And so essentially, what we're talking about here is, this is a Mellanox product called as ConnectX-5, but we have a family of NICs, smart NICs called as ConnectX as well as Bluefield. ConnectX is there's a definition of a smart NIC in the industry, which is a purpose-built hardware, but it also has a processor on it. So that's something that we call as Bluefield. ConnectX here is our intelligent NIC, we call it. Now, you argue with the name, but let's not get into that. Essentially, what it has is, it has intelligent networking offload capabilities. So not only can it do 10, 25, 50, 100 gig, and the ConnectX 6 that's just out a couple quarters ago can do 200 gig per port, right? And in addition to all of that, it can do a lot of acceleration features. So for example, you can do completely OVS hardware offload into the E-switch of a smart NIC, and we'll talk more about that in a second. You can do NCAP, DCAP for overlay networking. So Mark will talk about how we achieve that in an E-switch of the NIC. We can do RoCE, which is RDMA over Converged Ethernet, which is a really efficient protocol for transferring the data between two applications on a lowest latency basis. Really great for edge data centers. So all of this is plus the SRIOV, which is a basis for a lot of high throughput kind of acceleration technologies. So all of this can be done in a single ASIC-based silicon, right? Which is the great news here, right? And that is why this is called as a cloud NIC for Mellanox, because it's been deployed in all of the cloud infrastructures out today. So let's recap what is OVS hardware offload. Now that we know the product that can do this, which is the Mellanox CX5, we can also see the OVS, how it can offload this to the E-switch of the NIC. So traditionally what happens is in SRIOV, forget the OVS part for a second, you can get a really great throughput by sending the packet pretty fast from the NIC itself over a virtual interface that is connected to the VM. So you have the H0 and the VH0. Those are the counterparts that are talking to each other. But what's happening is the SDN control plane information of visibility is missing. You do not have the OVS talking to the SRIOV. And so that's why SRIOV is not really a SDN-friendly kind of protocol, right? But then what we did is the community came together and said, okay, how do we make sure that we do not still sacrifice the throughput you get because of SRIOV? So now the community added the OVS hardware offload technology, basically, or the API to do that, to program the E-switch of the NIC from the OVS. And that is what is being done as OVS hardware offload. So what happens in the OVS hardware offload technology is you get the faster data path from SRIOV, and then you also get the OVS programming into the E-switch for all of the control plane traffic. So all of your flow rules, et cetera, are offloaded from the OVS into the E-switch. So you get best of both worlds. So you can have your cake again and can eat it too because you got best of both worlds. In terms of the packet flow, normally what happens is OVS has two counterparts. One is the user space and one is the kernel space. But when OVS is not offloaded, the packet normally traverses all the way to the vSwitch-D, where the rule will be kind of programmed into the OVS kernel. And then the subsequent packets are going through the OVS kernel. But that's still eating up a lot of CPU. It's slow. And so with the E-switch, where you have the offloads now, the rules are offloaded all the way to the E-switch. So you're getting the fastest fast switch path in the hardware offloaded manner. This is the day in the life of a packet. Okay. So typically what happens is a packet comes in, and this is in the SDN model. This is not the traditional model where, this is the open flow model, where you can see that a packet arrives, and what happens is the packet gets classified into flows. And how does that happen is through the number of tuples. And you can have 5 tuples or 7 tuples to classify your packet. Oops, something is going on. Is it okay? All good? All right. And then the packet, based on the flow classification, what you do is you do a match action. So you match the flows, and then you say, okay, what is the action that I need to take on this? And that's pretty much the same mundane work that you do. Now, you wouldn't want to do you wouldn't want to do this kind of work into a general purpose processor, right? It's not really purpose built for handling this thing in an efficient way. So what you do is with the E-switch or the Mellanox OVS offload technology, you could do all of this classification by doing the match actions, by doing the matching on each of the packet that comes in. And then you can decide the actions, which could be drop the packet, for example. Can you forward the packet to another port? Can you rewrite the headers of the packet? That means a distributed virtual routing, something that Nokia Controller is really famous for. You can do pretty much layer 2 switching in the E-switch of the NIC. You can do overlay networking, NCAP, DCAP. You can do telemetry. You can do increment, decrement counters. All of these are different functions that are being already added or been part of the E-switch that's out there. So it's really great that you can do all these functions in a single small form factor NIC that has been purpose-built for this purpose. And not only that, you can also do all these functions that are the building blocks, the matching and actions. They will help you to realize the functions that are NFV functions, so load balancing, virtual switching, firewall, DDoS, monitoring of the network, traffic analyzers, et cetera. One thing to remember, though, is that people think about DPDK and ASAP squared or the OVS hardware offload technology being similar or kind of the same. That's not the case. DPDK is Data Plane Development Kit, which is a technology which is software acceleration based. You use the software, you use the CPU for accelerating the workload performance, right? And the CPU does the work in a DPDK. Mellanox has really great performance for the DPDK NICs, for the DPDK part of the acceleration. We do 148 million packets per second on our 100 gig NIC. But at the same time, you do have to lock up the CPU cores for doing the polling in the DPDK because there's a poll mode driver that's been used for DPDK. Unlike ASAP squared, which is the OVS hardware offload technology from Mellanox, and it's called as accelerated switching and packet processing, you do not involve the CPU at all. You offload the CPU completely, and your NIC does all the work. The NIC, basically the E-switch will do all the work. And it basically gives you even better performance than what you can get on DPDK. You can get up to 8 to 10x performance better performance. And then also the CPU is not being utilized. So that's really great in achieving better performance without using the CPU cores and better efficiency. This is supported across our SmartNIC family, Bluefield, as well as the ConnectX 5. So let's move into the numbers here a little bit. I will not go into all the details, but essentially with DPDK, if you run OVS over DPDK, you can get for 2 cores up to 7.6 million packets per second. Versus with OVS offload technology, hardware offload technology, or ASAP squared, you can get, for 0 CPU, up to 66 million packets per second. And this is all on a 100 gig card, right? So you can extrapolate the numbers on a 25 gig if you like. But essentially, one thing to note is OVS hardware technology is not a vendor-based technology. It's a open source, it's an open technology that's been enabled in the community. There's a blueprint for that in the OpenStack. There is integration with all the leading platforms such as Red Hat, Nuage, in the vanilla OpenStack, OVS, all these communities, Linux communities. So it's not a vendor locked-in solution. It's just that the silicon happens to be hardware, but hardware has to have something that's its own. So just to recap on how's the OVS hardware technology, how's that integrated, where is it available? It's available in the kernel 4.8 plus. So if you have a kernel 4.8 plus, that's what you need minimum. You need an OVS 2.8 plus for that. You need minimum Queens release, OpenStack Queens. Mellanox Connect X4, X5 are definitely supporting this. There are a few other vendors who might support it as well, but Mellanox is very well known for this work. We pushed a lot of upstream work to do this work in the community. Red Hat 7.5 plus or above, and Red Hat OSP 13 and above, and Nuage Networks VSP 541. These are the kind of platforms that you can use on the commercial side as well as on the open source side of things. So with that, I'm going to hand it off to Mark to talk about Nuage Networks and provide a good demo of OVS hardware technology.
Okay.
Thank you, Mark.
Yeah, thanks. So actually, altogether, we're going to show 3 different demos here today. The first one will be an OpenStack demo in which we actually show how all of this OVS offloading onto an E-switch on the NIC is actually working and how the integration has really matured. So let me just say, this is actually, amazingly, the 4th time we've had a chance to come to OpenStack and present a little bit about the work we've been doing and about enabling the E-switch on NIC. And I think the real breakthrough actually happened a year ago in Vancouver, where we were able to show that like real VXLAN flows could truly be offloaded and you could get stellar numbers in terms of performance. But since then, it's not about performance. It's really about all the integration. It's about making all the features work. It's about the use cases that real service providers need to have and automating everything. And so a lot of the build out that's been going on over the last year or so really focuses on that. And so today, what I'm going to show is OSPD deployed OpenStack and how it actually implements and utilizes the E-switch using an Ixia as a load generation mechanism in a context that's much more like a real production environment compared to things we've done in the past. So first, let me just briefly say that Nuage is a SDN provider. Our SDN, like many other SDNs, is pretty much built around a 3-layer architecture. So you have a management layer, a control layer, and then you have OVS or something like that, actually programming each compute node and taking care of the switching and routing that goes on for the packets where the rubber meets the road. And the only change, or the significant change that's happened here to enable our product to take advantage of eSwitch is modifying the OVS that we're using. So basically taking a lot of the TC functionality, TC flower functionality, and enabling it inside of our OVS, which we call VRS. So that's the kind of the architecture in terms of how we're programming the flows. In terms of how this actually happens, in terms of programming, there's really 2 secrets. There's shortening the data path by using host pass-through, so a virtual VF, a virtual function, which is actually a partial PCI device, gets passed through or tunneled to a VM. And then the other piece that goes on is putting in a representer to talk to the OVS switch and take the programming information and associate it, so the flow programming information, and associating it with the particular VF that's being used by that particular VM. So the representer actually makes the chain of connection between the SRIOV pass-through that's happening to the VM and the program that's being done by the SDN controller. So in our test environment today, we're going to be looking closely at a single compute node that's been deployed on the overcloud by OSPD 13. So that is the top box. And in the top box, we have test PMD running. For those of you who are familiar with DPDK, I'm sure you know this forwarding app. It's pretty ubiquitous. So that forwarding app will actually have two interfaces, and we're going to be running both of those interfaces bidirectionally. And then the test PMD resides inside of a host with a ConnectX-5 NIC, and we're feeding that NIC through a Tor, which is actually performing VLAN trunking. So we have an Ixia load generator, and then that generates VLAN packets, which are then translated into VXLAN and then presented to the host. This may seem a little convoluted, but this is actually kind of mirroring some typical environments you actually see. And the important thing for us is that we're seeing essentially zero packet loss, even at roughly 80 or more % of line rate. So in this test, then we have two different legs. They have different IP addresses, and I've kind of laid that out here. With that, though, let's go ahead and jump to the video. And I'll just talk to this as it kind of goes by here. It's slow. I'm sorry. I got just a little too much preamble here of nothing. Oh, it's not coming out on the screen? Okay. You want me to turn my laptop around so everyone can see my laptop? Help, guys. I don't know.
Yeah. Just maybe detach again and try again connecting. That's the last thing. I don't like. Are you in extended? Oh, there you go. It's just not showing up now. Probably. Nope.
You might drag the window over.
Drag which window?
Once the video starts.
But I don't understand. What window do I have to drag?
Well, whatever in the video, when the video is playing, you start it. So drag that whole window over.
Or just say share on both sides, right?
Or yeah.
This function F7.
Yeah.
Can you share on both desktops? There might be two desktops, right? Click function F7. Function F7. Let's say duplicate. There you go.
Oh, much better. All right, sorry.
I don't want to power off. Okay, good.
Are we good? All right. Okay, so as I said, I'm going to take you briefly through how all this stuff actually gets deployed in an OpenStack environment. It's very similar to some of the things we showed in Berlin. Important differences here, of course, so the data path is much more complex this time. And also, all this has been deployed with OSPD, so it's truly an automated environment. And that's really, really important when you're deploying like thousands of systems. So I'll start out by the view as seen by the Nuage SDN controller, or by our GUI essentially that maps things out. So we're looking at the different networks that have been provisioned. So our ML2 plugin is bidirectional. You can create networks either with Neutron, or you can create them with our software, and then the other side is actually reciprocally created. So here you can see very complex names, which tells you that the networks were originally created by OpenStack, and then they showed up here as subnets and as vPorts that are being managed by the Nuage SDN. Okay, and these vPorts that you're seeing here are the ports that are being used to feed test PMD. Okay. Now we'll take a look at the OpenStack controller, and we'll focus on test PMD, which is the primary VNF that's been deployed here. It's really the device under test, so hence the name DUT. So we'll look at the properties. You can see it has two different networks attached to it, and they're running on two different networks. These are virtual networks that ride on top of a physical network that's been provisioned, as I showed earlier. Okay. And the important thing I wanted you to see here is that the vPorts that are being attached to the VM to test PMD have both the direct interface enabled and also have switch dev configured for that port. Okay. Yeah, it's just opening up now. This is one of the vPorts right here, and you can see near the bottom VNIC type is direct, and profile is switch dev. Okay. Now we're going to jump to taking a look at the Ixia setup and how that was provisioned. Yep. So here we have two different legs that are both being generated by the Ixia, leg 2 and leg 1. Each one has its own unique address space. And we're going to program each of these legs to run at, I think it's around 7 million packets per second. So that means there's a total of, since there's two different flows, 14 million packets being received on both interfaces inside of the test PMD. Okay, we'll have a quick look here at what's actually in the packet. These are UDP packets. If you can read the fine print, it's a 128 byte frame. So it's just shooting bullets basically at test PMD, and test PMD is just doing a max swap and sending them back on the other interface. Okay, and now we have everything running. You can see each one of the legs is running around 7 million packets per second. You can also see the percent loss. Actually, we'll have to refresh the stats here in a second, but there's zero loss going on. Here we just dumped the flows. We're looking at this from several different perspectives, but you can see that the OVS flows are offloaded. It's highlighted in red. And we can also do a watch on these flows and actually see the stats being incremented as the number of packets goes through. Again, a little bit hard to read here, but watch is highlighting the significant digits that are changing. So you can see for yourself that a large number of packets are being processed as time goes by. This is the view inside of test PMD. Oops, sorry, we're still a little glitch on my video here. Yeah. Oh, now we're looking at BMON. So we're using BMON, and you can see here the number of packets per second being received and sent is exactly 14 million on both sides, TX and RX. And that corresponds to about 20 gigabits per second, which is roughly 80% of the line rate. So that's really great performance. And you can also see the perspective from test PMD. Both links are showing essentially zero loss. The packet throughput is around 7 million packets per second within like 6 digits on both interfaces. So all the way through the cycle that the packets transit, there's zero drops. And finally, and maybe the most important point, we were watching the CPU utilization all the time that this was going on. So the percent utilization or the idle time is like 94%. That means 6% of the CPU was utilized constantly. And that's because test PMD is a DPDK app. So whatever cores you hand to that app are basically abducted by DPDK and are completely lost whether you have throughput going on or not. But when the extra throughput goes through the system, if you have VXLAN tunneling or detunneling going on, none of that impacts the host itself. So all that work is being handled by the NIC, and it's completely and fully offloaded, freeing up the NIC or the host to take care of useful computing. So end of demo. Okay. Current slide.
Am I on? Okay. So basically, you can see that the technology, the OVS hardware offload technology, you can use it in the core data center. You can use it on the edge. On the edge, it's even more important. As you can see, you can realize more efficiencies you can reduce your server footprint if you can have a technology that can free up the CPU cores, right? So that's the point here. The next one is we're running a little bit short on time because of some of the glitches we had, but I'm going to cruise through quickly. We're going to show the similar technology for OVS hardware offload for Kubernetes pods. using CNI. So I'm going to skip through some of the slides. I think you already know the kind of the gist here. What is a SRIAV? We talked about that, and how it can be done using how ASAP squared or the OVS hardware offload. How can we enable that using Nuage networks and Mellanox eSwitch in the intelligent or the SmartNICs. So basically, a demo will be just about that. I don't want to go into all the details, but essentially, in the container pods, you're attaching the ETH0, the net device, to the VF that is created on the NIC, and then it's all controlled through the Kubernetes CNI plugin for Nuage, and it's basically offloading the OVS into the eSwitch of the NIC. That's basically the gist of it. So with that, I'm going to hand it off to Mark to go into the demo again.
Yeah. Okay. Thanks. Yeah, so the demo here is basically a Kubernetes deployment, which is going to have an accelerated data path. We'll have a couple containers that are running a user space iPerf application just to generate load, and also a netperf to take a look at latency. So as you can see from the setup picture here, there's one pair of pods that are using offload and another pair of pods that are not. So in the demo that I'll show, you'll see both cases, and we'll show different aspects of what's happening with the flows and the performance and so on. Okay, so with that, let's cross our fingers and hope we're more successful with the second video. Kubernetes. No, okay, F7. Yeah. Yeah, thanks. Yeah, okay, so we start out here by first giving you a view of the underlay as seen by the Nuage software. So we have 3 different compute nodes in the Kubernetes cluster. Each one of those has our implementation of OVS, which supports OVS offload. There are also ports and containers that have been deployed. And so you can see the physical addressing of these, and also the physical network ports that have been assigned to those containers. So these are VFs that have been created when we turned on SRIOV. Now we take a look at this on the virtual networking plane. Here, everything's disaggregated from. Oh.
What's going on?
Yeah, a bad video day. Yeah, okay. Okay, so here you can see the different vPorts that were created. Also, we're taking a look at OVS itself, the bridge that we're using that contains those ports. An important parameter that has been set here is the hardware offload is set to true. And so now we'll start some benchmarks. And again, we're just running simple things, ping, iPerf, and netperf here, just to demonstrate, more from a user perspective, what the benefit for containers is to having OVS offloading going. So here we're pinging, we generate some flows. You can see these flows are going through the non-accelerated path, so there's no hardware offload on these flows. That's really about the only thing you can derive from this, I'd say. Now we take a look at latency using, well, okay, so we ran iPerf here to get throughput, so around 14 gigabits per second, unaccelerated. And now we're running netperf and measuring the latency for UDP packets and then also TCP packets. And I'll summarize the numbers at the end. Now here, we've switched over to the configuration that has the offloading enabled. And if you do TCP dump, you only see packets one time, because after the first time, the flow is learned, and all the flow processing is happening in the NIC. So you're never even seeing any of that stuff find its way up into the kernel until it gets to the container. And whatever goes to the container is direct. So even that is missed by the kernel, the host kernel. And we take a look at throughput with iPerf. Now it's up to 21.7 gigabits per second. This again using a 25 gig connection. Measure latency, both for TCP and UDP. And summarize the results here in a second. Yeah, so for throughput, with the OVS offloading enabled for a single container, a pair, we're seeing roughly 50% more throughput, and the latency was reduced by 33 or 35 to 40%. So things are getting through faster, which is good from a user perspective. And let me just stress, if we had done this with DPDK apps and the containers, you would have seen a much more accentuated benefit from the OVS offloading, because then it's really all about the throughput of the network, and the user space latencies and excess memory copies do not come into play. Okay, so with that, get you going from current slide.
Come on, yep. Okay, so we're a little short on time again, but it's essentially the third key technology that we want to talk about today. So we talked about A/2 or the OVS hardware offload for a OpenStack environment, for a Kubernetes environment, for the edge clouds, for any virtualized environment, basically. And then the third one that we want to talk about today is this cost-reduced network design for edge cloud, for the edge data center. And there's a technology that we are introducing for the first time. It's called as host chaining. It's been, so traditionally what happens is normally you have your servers that are connected to a top-of-rack switch, and each of the network port is connected to the top-of-rack switch port. This design, though, it's the standard design. It's pretty expensive because the cost of a port on a switch is much, much higher than the cost of a port on a NIC. So for smaller networks, what you could do is you could connect all these different hosts in a chained manner, so they can form different topologies. It could be a token kind of ring, kind of the old good token ring kind of topology, just a ring, or it could be a daisy chained host. So you can do that using the NIC itself. You don't need, this is not based on the E-switch, this is just based on the pure NIC, right? And we'll talk about what this technology is. Essentially, what it is with host chaining, the NIC forwards the packets from one port of the NIC to the next port of the NIC. So it's basically a hairpin use case. And why do you want to do that? You can reduce substantially the cost of using a switch port. Like I said, you don't even get a 4-port switch or an 8-port switch for a 2500 gig kind of switch ports, right? It's really, you always have to over-provision your switch ports, and that's pretty expensive. So for smaller networks, the contained networks, you may not want to even deploy a switch if you have a host chaining solution. You can use less power, cooling, and real estate on the edge side is very important because you don't have to have one switch up there, right? You can reduce the CPU burden again because the host chaining, the NIC itself will do the forwarding of the packet, and how that happens, we'll talk about that in a second. You don't need to use the CPU for doing the forwarding, for example. There's no change to how normally things are done from the host to the network. This applies only from the network to the host, okay? This is what the host chaining solution is. Some of the use cases are distributed packet processing. So you can have this host do distributed set of services on their own. So maybe an appliance-based model, but it's all virtualized and distributed. It could be static service chains or well-defined service chains where you know the packet has to go sequentially between different hosts. Or it can be any sort of a daisy-chained network or a ring topology that you can create through this network, through this host chaining solution. And what it is essentially, like I said, it's if the packet comes on this particular port from the wire or from the network, you'll just check sure there's a port A and a port B. These are the two ports of the NIC. When the packet is arrived, you just make sure that you do a check of source MAC equal to A. That means if this is a loopback packet or a spurious packet that's looping back to your same port, then you need to discard that packet. But if it's not, then you just check is the destination MAC equal to the MAC A, the address of this particular port, then you send it to the host over the physical function. If it's not for this particular host, maybe it's for the next host that's connected on the second port. And so you can forward this to the second port, but you can again check if the source MAC is equal to B. If that's the case, then you discard it because it might be again a loopback packet coming for the B from the port B. So you'll discard that. If not, then you just forward it again to the port B, and then port B does the same check like port A to see if this is for host B or the port B forwarding to the port B, or should it just go out on the wire. So it's either a hairpin or going to the host A or host B. It's a very simple solution. It's a hairpin use case, basically, that you can use to create chain topology. Broadcast packet, you can handle broadcast packet similarly, just that in this case, when a packet with a, let's say, ARP broadcast, you'll get all FFFs. You can send this on every port, provided the checks are all fine, that this is not a loopback packet or spurious packet. Then you can send it to each of the hosts or each of the ports, and then also on the wire. So that's basically how the broadcast case will work. Host packet handling is not changed. Basically, when the packet comes from the host, it'll go and make sure that the host source MAC is set to the MAC of this particular port, and then the packet goes out as is. There's nothing going on differently about it. There's no change to the host packet. You can create, like I said, different topologies. You can create your ring topology because you have all these different hosts that are chained, and they're forwarding the packet either in the hairpin manner or they're consuming the packet. So this is the host chaining configuration. I'm not going to talk about that. Mark might show you a quick demo of that. But essentially, you can create a unidirectional ring topology where one port is doing egress or transmit, and the other port is doing ingress, which is just receiving the packet. You're transmitting from this TX to the RX of the next NIC, basically through the cable, and then depending on the host chaining rules that we just talked about, it'll either consume the packet or forward it to the next host. And that's how the chain will go. It's a unidirectional chain in this case. You can also create a bidirectional chain, just same thing as the unidirectional one, just that it will have two ports that are both receive and transmit at the same time. So it's a full duplex, bidirectional chain. The blue chain is basically one on one IP, one subnet, and the brown or whatever this color is another subnet, right, on another chain, basically for that. With that, I'm going to hand it off to Mark to kind of wrap it up.
Yeah, okay, thanks, Ash. So yeah, I had a little demo here, and at the beginning, I wanted to show you what like a typical edge configuration looks like. Real estate is really an issue. You know, it's really painful to stick a full Tor into an edge configuration similar to the one I'm showing here in the picture. At the same time, there's requirements for low latency. There's multi-tenancy going on. There's a lot of other things that need to be met, and there needs to be continuity of policy and communication between the edge and also the data center, wherever your compute is being hosted. So in this demo that I'm going to show here today, we'll just have a simple virtual machine running here on a three-node ring, and I'll basically show first what the latency looks like on the underlay, just showing that the ring is really not contributing any difference if it's one hop or two hops. And then after that, we'll just show that you can do VXLAN tunnels between the different nodes here. And those VXLAN tunnels could as well incorporate applications that are running back in the data center as well as applications that are running on the edge itself. So with that, I'll just jump to the demo. And again, we're logging in. Just so I give, to start out, I'll give you the underlay perception of things as seen by the SDN controller. So we have one SDN controller, and then there are three nodes here that are ring nodes. So these nodes are not directly connected to the, through a switch to the controller. They're coming in through the ring. So the packets actually transit through the ring, and then they go through a cloud of some kind. In this case, it's just a switch. And then they eventually make it back to the controller. So everything's controlled from the data center, but the rules in terms of how packets are exchanged on the edge are determined by the policy that gets pushed down. And so you can see here the different ports that were created. You can see the IP addresses of these ports are 1010.0.111 and 1010.0.131. So 111 is on the first edge node, and 113 or 131 is on the third edge node. Okay. And here I'm just showing you the IP address of one of the edge nodes, the first one. Then I'll connect to the second edge node and then the third edge node. So again, these things are not directly connected back to a switch that's going to the controller. They're only coming in through the ring itself. So they transit through the nodes. And the genius of all this, by the way, is that what Mellanox has implemented is this forwarding application that recognizes what packets should belong to a particular host, if they belong there, they're pushed up to the host. Otherwise, they just push through. So there's no tax or there's no compute burden put on the host in order to forward packets. And the typical latency for one of those forwardings is around 320 nanoseconds. So it's really fast compared to anything that would happen in user space. And so, you could have quite a few hops before you'd really have any impact from taking away the Tor. So here I'm just showing iPerf running between the first hop, and we're getting a throughput around 21 gigabits per second. This is on a 25 gig link. And then here we're doing the same thing again, but we're going through 2 hops. And the throughput is essentially the same. It's right around 21 plus gigabits per second. Okay, and then finally, the last thing we'll do is take a look at throughput as seen by VMs that are actually running in this environment. So this is a VXLAN tunnel that's going through the ring. That VXLAN tunnel could also be extended back to a data center through a switch. And once again, you can see these are overlay IP addresses that I called out earlier. So there's 1111 and there's 131. One's a VM on the third node and the other's a VM on the first node. And we run iPerf just to see what's going on. And what you'll see is the throughput's, it's quite a bit less because you're going through all the other delays that happen as a result of the user space and VirtIO and the memory copies that have to happen. Now, all that could be shrunk and done away with if you could enable the switch dev on NIC. Currently, that's not allowed while you have the host chaining going on. And the primary reason for that is that they're concerned that if you have a lot of VFs and you're allowing packets with multiple source MAC addresses to get out onto the ring, the system won't be able to keep track of that with the forwarding app. But in our case, since we're doing VXLAN encapsulation of all the traffic coming through those VFs, there would only be one source MAC address. So conceptually, it should be possible to turn on the switch on NIC and also do this kind of host chaining and shrink the edge compute platform.
All right, that's it?
That's it.
Okay, thank you for waiting for a little bit more. Appreciate that. Hope it was useful. Thank you.